Yeah, let's keep continuing um, how to treat the equilibrium systematically. Here is a quick tip, okay, from the textbook. So to treat equilibrium systematically, you may take these these steps. First, write the pertinent reactions. Okay, when the question is given, then you have to write the pertinent reactions as many as possible. Okay, it is depends on your knowledge on chemical reactions, but after practicing, and then you can write pertinent reactions. And second step is to write the charge balance equation. This is quite straightforward. Okay, from the the pertinent reactions, then you can identify which species are charged, okay, positively and negatively charged. And third step is to write mass balance equations. There may be more than one, okay, and you have to find out the mass balance equations, okay. May, in many cases it is only one, but uh, there are more than one mass balance equations, okay, and sometimes the mass balance equations are the same as the charge balance equation, okay, that's okay, you see. um, and then if the same mass balance or charge balance equation um, is obtained, of course you disregard one, okay. And the next step is to write the equilibrium constant expression for each chemical reaction. This step is the only one in which activity coefficients appear, okay. And then for those pertinent reactions, you find the chemical equilibrium constant, okay. And what if you don't have any equilibrium constant? Then it is very difficult to solve the problem. But usually, the pertinent for the pertinent reactions, the equilibrium constants are known. Okay, so but in this expression, you have to use, you need to use the activity coefficients. Okay, this is only a step in which the activity coefficients appear. Okay, but as you will know later, the activity coefficients are simply ignored. And the next step is to count the equations and unknowns. As I mentioned in previous lecture, um, the solution is only one, so all the problems um, are bound to be solved. Okay, that means the number of equations is the same as the number of unknowns. So there is only one solution. Okay, here there should be as many equations as unknowns chemical species. If not, you must either find more equilibria or fix some concentrations at known values. Okay, and then finally you solve for all unknowns. Okay, steps 1, okay, writing chemical reactions, and step 6, okay, solve for the all unknowns are the heart of the problem. Guessing what chemical equilibria exist in a given solution requires a fair degree of chemical intuition. Okay, yeah, so actually solving uh, this kind of problem is not simple. Okay, but in principle, all the problems, okay, must be solved. Yeah? Because there is only one condition after reactions. So okay, that's why so we can solve the problems um, in confidence. Okay, the best way to um, apply the this systematic treatment of equilibrium is to actually solve some examples. Okay, here is the first example. Applying the systematic treatment of equilibrium. First example is to find concentrations of species in 0.01 molar solution of ammonia. Okay, so you dissolve the gas ammonia. Okay, and then now the solution concentration is 0.01 0.1 molar of ammonia. Okay, so the first step is to write the pertinent reactions. Okay, of course, ammonia dissociates in water. Okay, ammonia reacts with water and um, gives ammonium ion and hydroxide ion. So that's why ammonia is um, basic. Okay, basic species. It gives rise to hydroxide ion. All right, and then for this reaction, the equilibrium constant Kb is well known, which is 1.76 times 10 to minus 5 at the room temperature. Okay. Another pertinent reaction is this one, water dissociation. Right? This is kind of default in aqueous solution. Okay. Water is a solvent. It all the time undergoes water dissociation. Okay. It gives rise to proton and hydroxide ions, and Kw is 1.0 times 10 to minus 14 at room temperature. This one, this water dissociation is always there, so you can write, automatically. All right, and then let's find charge balance equation. Okay, and then you identify the cations and anions. Cations are two. Okay, ammonium ions and proton ions. Okay, since they are monovalent. Okay, the concentration, the sum of concentration is by given, by this one, and there is only one anion, which is hydroxide ion. Okay, this is the charge balance equation, very simple. And then mass balance equation, you have to find it. Okay, this one, original ammonium concentration. Okay, this one dissociates into this one. Okay, so after equilibrium, the ammonia molecule exists as either this one, undissociated form NH3, or as this ammonium ion. So total concentration, which is 0.01 molar, becomes equals the sum of the this one, ammonia concentration and ammonium ion concentration. Okay, this is the mass balance equation, and there are no more mass balance equations. Okay, and then we write the equilibrium constant for these two. Okay, here Kb can be written by this equation. This is from the definition of equilibrium constant. Here you use activity coefficient for ammonium ion, and then you write here gamma. The activity coefficient for hydroxide ion, also you add this activity coefficient. But for the ammonia, although you write here, actually for the neutral species, activity coefficient is 1. Okay, likewise you use the activity coefficients for proton and hydroxide ions. Okay, and then you count the number of variables and number of equations. It should be the same. Okay, how many variables are here? Okay, you count from here. Okay, which one? Ammonium ion, proton ion, hydroxide ion, and more, and another one here. Okay, ammonia. Okay, so there are 1, 2, 3, 4 variables, and how many equations are there? It must be 4. Okay, so 1, 2, 3, 4. Okay, so four variables and four equations. They are solvable. Okay, that means the solution is only one. Okay, there should be only one solution. But in most cases, okay, these activity coefficients are simply ignored. In other words, we consider this activity coefficient simply 1. Okay, but the next example, you will see how we use activity coefficient. But for this example, simply ignore activity coefficient, and then let's just try to solve these four equations. Okay, here is the one, and rearranging the equilibrium constant for this one, ammonium dissociation, and uh, this water dissociation, and then if you combine, you get this one. Okay, this equation. Now all the detailed explanation is given in your textbook. Okay, so we try to simplify, okay, the equations. And here, from mass balance equation, the ammonia concentration equals the formal concentration minus ammonium ion concentration. Okay, here the expression for ammonium ion concentration is given by this one, and then substitute into this ammonia ion expression. Here you get this equation, and then Kb is given by this one, and then you also substitute this one, the expression for ammonia concentration into this Kb equation. Okay, here. Okay, and ammonium ion concentration, you use this one. Okay, now this expression seems very complicated, but here we will use kind of simplification. Okay, since ammonia is dissolved in water, pH increases. Yeah, because ammonia is is a species that makes the solution basic. Okay, so in basic solution, usually hydroxide ion concentration is much greater than the proton concentration. Okay, the for neutral species, the pH is 7. All right, and the proton and hydroxide concentrations are the same, but if you increase the pH 1, okay, to 8, and then the concentration difference becomes what? 100 times. Okay, let's say pH is 8, and then hydroxide ion concentration is 10 to minus 6, and proton concentration is 10 to minus 8. So difference it becomes 100. Okay, but actually, although ammonia is a weak base, but it makes pH increase at least by 3 or 4. Okay, so the difference, the concentration difference between hydroxide ion and proton ions are great. It's very high, easily a million times different. Okay, so here we apply this approximation here, and then we simply ignore the proton concentration here. Okay, here this is hydroxide ion concentration, and this one is proton concentration, and then ignore. Okay, we can remove this part, and here also we remove this part, and then this expression becomes quite simplified. Okay, like this one, right? And then after rearrangement, this one, finally we get this quadratic equation. Kb is already known, and it is given by this one. This is quadratic equation, so the solution can be easily obtained. All right, yeah. Yeah, that's the trick. Not that's the strategy. Okay, not trick. I'm sorry. Okay, I strongly recommend you solve this quadratic equation. Okay, by applying Kb is already known, and formal concentration of ammonia is 0.01. Okay, so it can be easily um, solved. Okay.